just thrown a huge amount of stuff at you in 5 slides. I think maybe that's appropriate because life is complicated. And we said that if we want to avoid the mistakes of the past, we don't want to oversimplify by ignoring things at the beginning. We want to look at it all, and then we want to see what looks like it doesn't depend on chance, and we want to let universality and stability be our guide. So we've been able to boil the story down to focusing on the core molecules of biochemistry and what we use to build our own biomass. So at this point, we're still in the middle of a treasure hunt. We think we know what we're after, but there hasn't been an aha. That's for the next slide. But here's the cool thing. If you were to watch a movie and one of the characters were to open up a treasure map that has 5 arrows pointing to some place saying, here it is, this is it, you would say, okay, that's not a very subtle movie. What kind of a character needs that? What I'm about to show you is that the map of biochemistry is a treasure map with 5 arrows pointing to here it is, and it's been known since the 1960s. But people only started to recognize what they were seeing within about the last 25 years. So this is what is universal about the way we build all of our biomolecules. Biochemistry itself is not super complicated. If you ask what we are made of, we're made of 5 classes of things, and we know all of them because we have to eat them. Because you remember I said we're metabolically incomplete. So we need the fatty acids because otherwise we can't make cells. That's your olive oil. We need the amino acids, which we know from meringue and marshmallow and things like that. That's the structure and the enzymes and all that good stuff. We need sugars. Turns out they're probably more important for structure than they are for energy storage, but we like them for the other thing. Very, very important set of about 20 to 30 little molecules which do all of our sort of super fine chemistry, like the chlorophyll that allows plants to capture sunlight, or the heme that allows us to do respiration. And then, of course, there are the nucleic acids, the molecules of heredity. Now, there are 250 or 300 basic molecules that these are built up from. But here's the kicker. Every molecule in every living thing in all the world for all time has been synthesized from one of these 11 molecules in this cycle. Now, when we were in high school, a lot of us were taught about the Krebs cycle. And, of course, there was the $1 million, billion-dollar point here, which was ignored, and something of almost no importance that we were told. We were told that the Krebs cycle is important because we use it to break down sugars to get energy. The Krebs cycle is important because everything in the entire history of life has used it as the starting point to build every biomolecule, no exceptions. We came along 2.5 billion, well, single cells came along 2.5 billion years later and used it to get energy. But we're borrowers in that sense. So, it may be obvious now that I think this is where life started, but now that we have this chemical framework, I can also tell you why I think life had to start this way, which is a question that we can ask in chemistry in a way that we could not before. So, in biology, the struggle has always been, when you think in terms of control, how do you explain why something is there? Because when we think why is something there, we always think, what is it good for? Well, what is it good for is a purpose-based question, and it's not clear that it came up because it was good for anything. It came up for a different reason. In chemistry, we're not so susceptible to that error, because in chemistry, we're used to saying, what was it getting away from? So a new way to ask about why life emerged is to say, what was wrong with a non-living Earth? What was so wrong that could have driven it to have to change? And why was that change in the direction that led toward life? And that's the thing that I think we can answer, or that we can at least pose good questions to that are testable in the laboratory. So that's what I'll tell you about in what's left. Turns out, what we appeal to for understanding is the thing that's the most familiar of all. If you put enough stress on something, it will break. And it turns out that the essential math and also the essential intuition I care about for the origin of life is the intuition of breakdown. Now, the thing that might be or sort of counterintuitive if you've been wondering about the origin of life, you don't normally think of the origin of life as the breaking of a lifeless Earth. So the two things that I have to show you is, there's more than one way for things to break down. And then second, sometimes the process of breakdown is a process of creating new structure and creating accident where there was only formlessness before. But you'll be surprised. As familiar as crack propagation is to us, these other two facts about breakdown are equally familiar. One of them we know all the time, because lightning, of course, is a breakdown of the atmosphere. It's not a mechanical breakdown, but instead, it's an electrical breakdown. The thing that we need if we want to understand why life emerged is to understand where the stress came from and why it results in one kind of breakdown instead of another. So, if you want to understand lightning, you say that storm systems pull charges apart between the clouds and the ground, and that creates an electrical stress for the charges to try to recombine. The ordinary dry atmosphere, which is the preferred configuration, can't do that transport. But the creation of the plasma channel of the lightning bolt can do that transport, and that's what sustains the plasma channel. Now, we can't predict exactly the track it will take. That's contingent, that's accidental. But we can very well predict the chemistry of this plasma channel. So the analogy here, and it's better than an analogy, it's a scientific equivalence, is that our biochemistry is like the altered state that is the plasma channel within the lightning bolt, and it was driven into existence in something like the same way. Now, lightning is not an ideal example here because it's gone in a short time and we don't think of it as lasting for very long, even though on the scale of the processes that make it, it's plenty long-lived. But there are other examples. Hurricanes are another kind of a breakdown of the atmosphere. This is not a breakdown of the electrical structure of the atmosphere, it's a breakdown of the thermal structure. What I'm showing you here is a set of hurricane tracks which you can see transporting heat out of the tropical oceans and into the temperate and polar upper atmospheres. This is what drives the hurricane system, as of course people now understand and appreciate in a way that they didn't a little while back. This is a channel that has the ability to pull in heat in order to reinforce its own structure, and the wall storms of the hurricane are transporting that heat from the ocean to the upper atmosphere. But in order to do that, they have to break the smooth layered structure that the atmospheric temperature usually has. So, if we want to understand the emergence of life, was it a chemical breakdown? What we have to ask is, where did that happen? And what was the stress that would have caused it to happen? And now we're talking about stress in a chemical sense. So, my good friend and colleague Harold Morowitz, who is much older than I, also has an infinite gift for words. And he has recognized, that's why he's written something like 8 or 9 books that are revered around the world, and I recommend any of them to you. But he's recognized that theories of the origin of life can be divided into 2 categories. There are the heaven theories and the hell theories. You can already guess which one I'll like. But it turns out that this has a basis. They're distinguished according to where the energy comes from in the life forms that use it today. The heaven theories are all of the theories whose energy ultimately comes from sunlight or starlight. The idea is that there's so much energy in this that it can do the chemistry of forming carbon-carbon bonds. So it can produce the small molecules. This can happen on the surfaces of asteroids, which then fall on the Earth, can happen in the ices of comets. In some small amount, the sunlight drives the weather system, and a little bit of the energy from weather winds up in the lightning bolt, and that can do a little bit of chemistry. This was what the Miller-Urey experiment showed that was so exciting to people and that got the origin of life started as a scientific question. And all of these stories that have to do with this sort of sunlight-yielded chemistry are the things that we associate with the primordial soup. Now, this appealed to people when there was no other idea in town, but there are a lot of problems with it. Sunlight is a tremendous energy source, but it's not easy to use because it tends to destroy things. And so, in fact, it's much easier to understand the way sunlight is used today if that happened somewhat later on when there was already life in place with the complex ability to capture it. Another problem with the primordial soup is that you need to finish life before the soup is done. So you're on the clock. The idea is that, in the classical scenarios, heaven deposits organic materials on the surface of the ocean, and accidental chemistry gives you a control mechanism, and then you have the keys to life itself, the DNA or whatever. But then you have to build the whole life underneath of this before you have used all of the soup. So that's unappealing. The thing that to me is the biggest problem with these ideas is that in this chemistry, there's no special place for the biochemistry we see. And there's no special reason to exclude all of the things that are not in our biochemistry. So it's not clear to me that this is very tightly coupled to who we are. And since the whole point of exploring biochemistry was that that was the thing to be explained, I think we should expect a coupling. And that's where the hell theory comes in. This is the theory particularly associated with hydrothermal vents. These can be volcanoes, but they can be quieter things that involve magma and water under the deep ocean. There can be many different kinds. You can have these guys which are alkaline and which are full of carbon dioxide, but not too much metal. These are called white smokers, and they occur in not the hottest places. These are about at the boiling temperature of water, a little bit cooler. These guys can be 600 degrees Fahrenheit or 300 degrees Celsius, roughly. And they thunder along at the bottom of the ocean. They're black because they're full of metal and sulfur. They're full of carbon dioxide. They're full of hydrogen. In particular, they're full of all of the chemicals that life needs to exist, but they are not full of primordial soup. And oddly enough, that turns out to be an advantage. And I'll show you why in the next slide. Oh, I should mention to you that there are whole ecosystems that live down here. The little gray guy that I told you can live all by itself with no other living thing, they live down here in this range. And they do exactly the chemistry I'm going to tell you, I think was being done 4 billion years ago before there was life. If you want to understand what was wrong with a lifeless Earth, then you say, what was the problem? Here's the problem. The geochemistry creates carbon dioxide, and it creates hydrogen. Now, hydrogen has electrons that it can give to carbon or oxygen, and if it were to give them, so you put as many hydrogens as will fit around a carbon to make methane, you put as many hydrogens as will fit around an oxygen to make water, that is the most energy that's available from this system. You look at this picture and you say, well, how hard could it be? Well, it turns out it's very hard. It's harder than any non-living thing can do at an appreciable rate. But living things do it with superb efficiency. So what life on Earth is today doing, among other things, these geochemical processes are generating all this energetic stuff. But it would build up and build up and build up in the absence of life. Life consumes it, provides this downhill run to lower energy molecules. So the idea behind the lightning strike is that this stress, when there was no life, built up and created a lightning strike through chemistry to make this possible. But what does that have to do with biochemistry? All I showed you was carbon dioxide and methane. Here's a surprising thing that's a little different than we're used to thinking of. I told you that there are organisms that live in these hydrogen environments, the reducing environments that give electrons. They're doing this chemistry, and they have essentially nothing more than biosynthesis. Their energy capture is very limited. It's much less than 1/10 of what any of us use up in the air-breathing world. The surprising thing is that in order to get from here to here, the best way is to go through the molecules of life. So what this picture is, you can think of this as being the chemical equivalent of a ball rolling down a hill, and it has the same mathematical meaning. What I'm showing you here is the starting point when no chemistry has been done, the ending point when all of the energy has been extracted, and across here is how far you've gone in transferring those hydrogens. It turns out that there are no ways through little molecules to go from here to here that are as energy efficient and simple as going through these molecules, which are the ones in the cycle I showed you. You don't need to worry about the names, but if you want to know why is there sugar, there's sugar because sugar is downhill from the stuff that makes sugar. If you want to understand why there's oil, including petroleum, it's because oil is on the way to methane if you have enough hydrogen to make it. And so what I'm telling you the chemistry was doing here is exactly what these little guys are doing at the base of that hydrothermal vent that I showed you. And incidentally, if I had remembered to point it out on the tree, you remember that some of the organisms seem to connect in very, very close to the root. Unlike us, we're kind of connected way out here in the leaves. This is one of them. This connects all the way down at the bottom. Lives a few degrees below the boiling temperature of water. Seems to have ancestors that could be at least 3 billion years old before it has a common ancestry with anything else. Does this simple chemistry, is completely self-contained, and does nothing else. So this is the kind of model we're looking at for the chemistry of the origin of life. Now, you shouldn't believe me yet, even if you might believe me in a minute, because I just told you that all of this chemistry is hard. So where did any of this stuff come from if it's so hard to do? And that's what's special about the cycle at the core of biochemistry with all the arrows pointing to it.